Okay. Um, yeah, so today my plan is to, get started doing some initial work on creating bots for my game BumperCoins. But first, let's do a leak code warm up. Wait, okay. Let's go to problems. Night dollar. Okay, I'm pretty sure I've done this one before. Today's question of the day. Yeah, I've solved it. Um, okay. Then what? I really want to do a warm up. I'll just choose something random from here. Refueling stuff, shortest bridge. That's probably just some breadth first search nonsense. Um, 600 questions to choose from. Okay. That's too low. I don't think I want to do that. These are all hard. Lots of hards. Okay, I've actually done a lot of them. Um, 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 wild parentheses string. Minimum moves to spread stone over. Okay, this is probably let's just look at the frequency of that. Okay, let's just start off with this one. Drink some coffee. Okay, so there is a hint if you want to take one. 2850. Wow, that's a large number. They've come a long way. There's no editorial, so that's maybe because this question's too new. Because sometimes really difficult questions with tough solutions, like they're not like that easy to write an article for or explain. They don't have editorials. You're given a zero-index 2D integer matrix grid of size 3 by 3. Okay, so the size is specified, representing number of stones in each cell. The grid contains exactly 9 stones. Can be multiple stones in a single cell. In one move, you can move a single stone from its current cell to any other cell if two cells share a side. So it means like northwest, like the 4 cardinal directions. Return the minimum number of moves to place one stone each cell. Okay, I like that question. Let's look at that. Yeah, the like dislike ratio is pretty strong in favor of likes. So then here, like, just everything is one except for these two. So presumably you want to go from here to here. So like 1, 1, 1, or like 1, 2, 3, like 1, 2, like the Manhattan distance between here and here, like dx. D row, d call is yeah, that much. So it's clearly 3. Okay, that's a good example. Let's see something else. So then everything that's 1 we don't really care about. It's kind of finished maybe. Oh, there's some smudge on my laptop screen. Let's just wipe that out. Okay. So here, you could like give 2 here and 2 here for 4. Okay. Alright, is there a third example? No constraints. Let's not see them, because sometimes looking at the constraints kind of suggests to you something. We know it's 9 by 9. Okay. We're telling the minimum, so how do we spread this most optimally? Okay, so cells are like 3 types of cells. 3 classes. Equals 1, greater than 1, less, greater than 1, 0. That's it. So then want to take those greater than 1 and move those a 0. Okay, so in one move, you can move only a single stone in its current cell to any other cell if two cells share a side. So, like, ultimately, so, like, it's not like we can move more than two. So I guess that kind of simplifies it into, like, does that make it, is that in, like, single stone in move um, implies question mark, like independence. Independent, or independent is the key word. So, like, let's see. So then what? There's two perspectives. Like, one, consider like the stones greater than one, the cells, and like how to disperse them. The other one, I feel, which is more maybe more natural, is like look at the 0 and like see like for the 0 which one is closer, and then kind of like take that. Um, so greedy approach. Look at a 0 cell and and fill it with closest greater than 1. Like here, the closest greater than 1 is 2, so then we could kind of do that. That works. Here, like we fill it from here. Here we fill from here. From here we fill from there. And that works. Now, is there any like problem doing this? Let's think of a 1D case where it's like 2, 1, 1, 1, 0, like 2, 1, 1, 1, 0. So like this case, right? So like from here we'd get the 1, like these both, and these both. So like 1, 2, 3. Got like this distance plus this distance versus this distance plus this distance, like 2, 1, 1, 0, 1, 1, 1, 0. So then first 0, or wait, sorry. So then first 0. 2, we cost 2. 0 we get from first 2 cost 1, 2, 3, 4, 5, 6, 7, 8, 9. So total using greedy strat is 11. Could we get this? Like, what if we get this from this and that from that? Like, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6. Okay, so it's still 11. Hmm. Hmm. Let's see. What if it's more than one dimension? More than 1D greedy? Like, let's think. So, like, we could have this, like, let's see. Like the reason I chose this example right here was like I wanted to say that like from the zero by taking this two right here to our left, like sure we get this, but then we might have messed things up for that one. Mm-hmm. Let's say we have like um, let me just take some while to think about this. Mm-hmm. Let's see on my whiteboard. So right here I put like kind of these three zeros and then like a three and a two. So like from the perspective of two, the closest zero to it is actually this one right here. Like these two, like are both 1, 2, 3, 1, 2, 3, like a knight's move in chess away. Whereas this one is four. So like greedy from the perspective of the source would mean that like this two would not be assigned to this one. It would be assigned to this one instead, one of these two. But like clearly, like these two want to be with this three because it's like right there, it can easily fill in. So that's like a cost. Like if we just kind of use what intuitively I feel is a correct strat, then from 3 to 0, 0, like that would be a 1, 2, 3, 4, 5, 6, which I believe could be the answer. Whereas like if we match two greedily to like let's just say this one, like 1, 2, 3, then that would be a cost of three, and then this three would still go here for four, and then you have to do this one. 1, 2, 3, 4. So like exactly. So then four plus like this is clearly greater than six. I don't even know how much this is, but okay, 8. So I guess like greedy from the destination zero seems to make sense. Cause like if you look from the source and like look at the nearest like kind of zero to it, if we kind of like pair this with like one of the closest zeros. The problem is that like there could be something else that wanted to fill in that zero too. But then if you look at it from the zeros perspective, maybe like is there some change? Like how come like if you look from here, the closest one is 3, so like this greedy approach seems to work if you consider destination from the perspective of the zeros we want to fill, not from the perspective of the things that want to be like dest versus the source perspective. So like given a zero in the initial input, like we want to fill it up from somewhere. Like it needs to get some, like at the end of the day, like it has to be filled up from somewhere. So I guess like you might as well just choose the closest thing that you can fill with and then fill with that, right? If you have a zero here and like we have like some like something like here and like something worse is like kind of here a bit further away, then like you might as well like just go for this one. Now could there be drawbacks with that? Just like we have a drawback from greedy from the source. Like could there be this greedy dust strategy having a drawback? What if there's a tie? Like what if instead of this 3 like we have like, or instead of a 3 like well, let's say we have like a 2 and like a 2. Now like there's a tie break, so like let's just say that we break it on this one, so like we take this edge. Then what if this one has a 0 that's like what if this one has a 0 that's like say kind of closer to this one, like kind of right right about here, right? So like that's kind of our thing. So in this 0, like we kind of break here, and then this one will be matched there. So it'll be like 1, 2, 3, 4, 5, using the tile like greedy scrap. Whereas in actuality, you'd want to pair this and this, which would be 1, 2, 3. So greedy both ways does not work. So greedy is a fail. Um, so we probably need like some dynamic programming or something else. Hmm. Interesting. Interesting. I remember doing a question similar, like kind of similar to this, called like nearest bikes or something like that. Um, so like, hmm, let's see, take we could like look at all the zeros and then like, hmm, I really want to click the hint right now, but um, you know, greedy doesn't work. So like in this case for greedy 0, like even though we like had a tie break on the closest one, like we chose this one ended up being more suitable for that one. Hmm. mean, one thing that's kind of interesting to note is like the size is only 3 by 3, like just 9. Like it's a constant, like it's a very small number. So maybe does that mean brute force could work somehow? Like ultimately, like everything greater than 1, we just take that number greater than 1, we subtract 1 from it, and that's how much surplus we have. And then like it's kind of becomes a matchmaking problem between all these sources and destinations. Like could we just test every single combination, like every single possible pairing, and just like choose the assignments that give us the best ones? Like just kind of brute force test all pairings. Um, is there some like divide and conquer dynamic programming idea? Like you take the grid, you break it up into like some chunks, like two halves, and like you solve them there. But then what about the cross pairing, the mixtures? I don't know. I mean, okay, how do brute force approach work? Test and then like, hmm, so then force algo for each and one. We have some minus one extra extra and for each cell at 0 we and 0 cells need to be filled. I'll let you for each type the 0 cells. Okay, let's say we have like the first 0 cell. We could the first 0 cell. We just kind of any one of these cells. We just kind of take something that's greater than 1. We just kind of do it, mark it as filled, and then just uh, just continue on, like testing that 0 with every like the 0 with every possible thing, and then continuing from there. Kind of like a backtracking approach. Mm. Mm. So like, why did this thing break again? Like the greedy thing? Because right. Mm. backtracking. For like stuff 0 cells, venom, and a pause. Pair the paused 0 cell with each of the source cells and recurse. Okay. Now, I mean, I could click the hint, but I kind of want to implement this, even if it's super naive, just to give an answer, because I've spent lots of time on this. Like, let's see how much time I've been spending. Oh wait, I'm not even sure how long it's been, but yeah, it's been far too long on this problem. Anyways, list, array, 0 cells, new, array list, whatever, then for int r, for int r 0, r is less than 3, r plus plus, the usual stuff, 3y, oops, nope. See if grid and cell equals grid of the row and the column, if cell equals 0, 0 cells dot add nth array r comma c, continue, and if the cell is greater than 1, then hmm. Uh, hmm. Like, I feel like you need a map of, like, the non-zero cells to everything else. Okay, whatever, let's just do this for now. and backtrack and pause. Zero cells. Return, backtrack, start at 0, 0 cells, and min equals x value, return min. Okay, so the min is the integer. I'm gonna copy this actually. Oh yeah, the grid is undefined. So then we've found potential source. Grid for C plus minus. And moves equals math dot absolute for 0 cells. Wait, no. Int enter 0 cell equals 0 cells of this position. Pause. So then this one would be a 0 cell of what? The row would be in the form of 0. And then the column. So that's how many moves we have. Then what? Oh wait, no, we can do this. Min equals integer dot max value. So that means that we never even found anything. Then we're already done. Else what we do is we just return min. Moves and moves plus equals to backtrack from position plus 1, 0 cells. That means like we can advance and grid. And it kind of recurs. And then what we do after that is we have to backtrack. And then what do we do here? And itself and moves. Something like that. Let's see if that works. Huh? Oh, right. Oh, right, at the end. If pass equals to 0 cells dot size, that means that we filled everything, we just return 0. Why do I feel like I'm gonna get a TLE time limit exceeded? I'll submit. Oh, wow, I actually beat everyone. Huh. Pretty much everyone did. Click description. Hint was 4 cells with more than 1 stone. Cells with 1 stone. Brute force. Yep. Brute force. Gotta be brute force. Because, I did the interesting cases. What I was thinking is a question called campus bikes, which I actually proved was suboptimal. But yeah, campus bikes leak code, right? And yes. This one, because I was on the Google list. Like this one, there's if m and n are typical dimensions, there's a mn log mn solution for this one, which I came up with. I think using a heap and using sorting, related topics. Yeah, sorting, but there is such an elegant thing where you can create extra data structures for each bike, for each worker, a list of bikes closest to them, and instead of mn log n, you can have mn log mn. You can reduce it to mn log either m or n, where one of them is the number of bikes and workers. But there's something really clever, kind of a whole bunch of pointers approach. At least I call it pointers, but if I look at the editorial, there's some really clever method for this. But anyways, the thing is, when I first contemplated this question, I remember realizing that this process, this greedy process of the shortest Manhattan distance, I remember convincing myself that's suboptimal. So anyways, yeah, I guess I did good. So then I think I'm ready to start now. Now that I'm warmed up, I'm pretty pleased that I got this backtrack correct in my first try, except I forgot obviously this edge case this base case right here, which was a bit disappointing, but overall, did good. So yeah, the whole point of this is to demonstrate or to create bots for BumperCoins. Now, one thing you can ask is what is that? So I mean, this is a game, right? In fact, I can actually show this game by showing some replays, like, or let me just or actually let's play a game against myself, right? Play. Let's open this in a new tab. Myself again. Play. Right. So I can kind of launch a coin here, launch a coin, launch a coin. If a coin hits the wall, it gets hurt a bit. Next tab. Now coins can collide. If two coins of different colors, enemy coins, hit each other, this inflicts damage here, right? And then if we just keep inflicting damage on an enemy, eventually this kind of halo represents its health, and at some point it'll go to 0, which means that it will die, just like that. So then there are these two special coins with stars, which means they're kings, and if we were to make this one go all the way to 0, then gold would win the game. Okay, let's just forfeit. And a replay for this game is being saved. So we can actually copy this replay and we can paste it right here to just kind of view the game. So okay, like that's kind of how it works. Yeah, if you look at this replay URL, which I'm highlighting right here, RDJ whatever, and like you, okay, that's cool, RDJ, and like you look right here, like kind of an actual like Firestore Google Cloud database. That's what's that like the data store for this thing. You can see a new entry right here in 928, and like this same ID right here matches this thing right here. That's like the replay system. Like if you actually look at the data, like basically this thing stores some data which kind of is a list of every single move that was done. So that's how it works. In fact, like we can look at some sample games that I played with someone else. Let's take like Dev is me. Okay, so I played this guy a whole bunch of times. And well, wow, this guy's been playing for quite some time. November 21. You also choose one of Lee's or Allele, I don't know. Let's just look at one of his games. Just kind of peek in on one of his games. Let's look at a replayer. Then let's just, okay, there's like a replay file too. But anyways, let's just watch this game. Oh, this guy's a pretty low rating. Oh, it feels like this guy stole his rating because they played a whole bunch. Okay, alright. Okay, there's a bit of conflict going on in both up and down of the board. This guy's trying to like kind of slip around the defenders to reach the king. I don't know why he's doing that. Okay, alright. Gold is attacking. The king is kind of stuck in this corner, getting bullied. Okay, interception, hit. Okay, so this silver player, Lee. Oh, this wind. He's using his wind to box in this king. That's called a coin trap. Wow, gold almost won. Alright, so this coin's almost dead, but it did a good job of weakening the king. I'll try to mount some counterattacks. It's a bit too late for that. Oh, he's kind of defending himself. Oh, it's going to be a king on king attack. Oh, he doubled it. Okay, very nice play by Yellow, by Gust. Yeah, there's something so satisfying like taking your king and like checkmating your opponent's king with your king, which is illegal in chess, but that's highly satisfying. There's also a maneuver being done. Right here, it's called the coin trap, where like these coins are boxing in this king. Like this is like walls right here. So right now, like this king is nowhere to move. He's kind of stuck by these ones, and then these coins can bully him. So okay, that's kind of the yeah, it's a common perform trap to trap your opponent's king in corners of the map. So that's kind of like a brief preview of the game. Oh, myself, I have 1244 rating. Did I gain rating from interesting? Maybe I just have a guest session with this much rating. Oh well, right. Can we like clear this somehow? Like more tools. I want to delete everything. Control A, Command A, or click it, Command A, delete. Okay, so that kind of like clears the board. All right. So how do I create bots for this game? Well, I kind of have to use the restroom right now, so I'll take a brief break. But for now, I'll kind of write some websites or show some sites that are super helpful for this stuff. But the main thing, I guess if someone wants to quickly catch up, is 3B1B B2. So like, yes, this thing exactly. I'm like, yeah, I watched. Like, he has a lot of good videos. Okay, I'm gonna use the restroom. Then we'll get on with the actual fun stuff, as in like uh make some like discuss the approach which I plan on taking for implementing my bots in this game. Alright, sorry for that. I'm back now. Right. Okay. Let's where's the notes? Yeah, here. Okay, let's write some notes. Okay. Alpha zero bots. So a few years ago, what I did was or let's get rid of the S. So like self play or wait no resources. Or yeah, a few years ago, I spent some time like studying, reviewing underwrite net, and in preparation for making bots. But of course, I got busy. I never got around doing it, which is why I'm doing it right now. But I'd like to review some concepts in algebra, like over and upper div, first semester, or like up to least squares, regression, and then multi-variable calculus, up to gradient, or as first half of the class, the differential half right before double integrals, integral half. So like for anyone that's watching currently viewers, they probably should have like taken at least multivariable calculus and at least one linear algebra class. Like I took two linear algebra classes, but like there's like a saying that like the second time around you revisit something, like that's when you actually learn it. And that kind of rang true to me. So yeah, I'll get some books. This one. This one. Um hmm. Alright. So so this right here, multivariable calculus by Stewart is like get a good kind of give it in the camera. This one right here is the I can see the author at the bottom by James Stewart is what I used many years ago in college for this class. Um, so in this book, you need to know up till chapter 14.6 inclusive. And then there's this book, which is a bit more abstract than like typical introduction to linear algebra. Like, there's like this like in my class the first linear algebra introductory course which I took it had differential equations too, and like it was really poorly taught, I guess. So like I actually had to like go to another schools. Like I used Khan Academy and like this Professor Gilbert Strang from let's write that down. Like Gilbert Strang. Oh, resources and 3B 1B. Actually, first I'll have like stuff I learned preparation for this. Uh, 10. B. Wait, no. Resources. Gilbert Strang's. For his linear algebra classes. Watch till placed squares. This guy's videos for basically everything. Oh yeah, and then finally there's another thing which I watched recently, like a few years ago. It's like reinforcement learning course by David Silver, up, I watched until, it stopped right after critic. Let's kind of Google this.
Okay.
Yeah, he is I like I actually watched his Essence of Calculus, all his videos. Like I originally saw them from Khan Academy as well, because like he did some work for them. But yeah, this course, and probably like anyone with some basic knowledge of multivariate calc could probably watch all of these in like within a day, and they're really good. So let's copy that and paste this right here. And then this one, I'll find it later, but yeah. Okay. So that's kind of what I expect viewers to, well, except for this is kind of optional, but it's kind of nice to, basically just takeaways would be like the, Bellman, uh, relation, or like, uh, policy iteration. Oh yeah, and actually the best resource, the best, alpha zero resource I found is like toy project, um, by, wait, let me check. Oh, sorry, his name is, Sarag. Yeah, Sarag. So like this thing right here, uh, this link right here, like this, this short, explanation of Monte Carlo tree search is, using kind of a nega max algorithm, like this whole negative thing, like in policy iteration, like all these, like this code right here and like this right here is, I expect this to be pretty invaluable, a low battery, so I'm just gonna charge it or connect it. Okay. Oh, and there's one other motivation, like, so let's begin. So for now, my voice is getting a bit tired, so I'll just focus on like a few derivations. Dot prod relation to projection, chain rule, gradient, significance, directional derivative, general, and then least squares, or just projection matrices. Which I'll use for least squares regression. So these are like the three things that I want to cover, and once I cover these, then okay, we can do that. Then like after we cover these, I'll dive right in and get started on bots. Actually, I feel this is a pretty good time to stop. Let's just cover this one for now, and then I'll probably end this live stream and take a break because I need to eventually eat some lunch. So dot product related to projection. Let me just save this, and then let's begin. I can just do everything in the whiteboard right here. Okay, let's start. Let's say if you have a vector A, and we want to do dot B. So like pretty early on, people learned that this is kind of like A and B are both vectors. So like, in fact, everything I'm about to say, there is a YouTube video that's kind of similar to this. It's called dot prod and projection duality, something like that. This one. Very extremely helpful video in case like my stuff doesn't make sense. Okay, so like you can watch, any viewers can, I strongly recommend them to watch this if they have almost any interest in linear algebra. So anyways, right, the whiteboard. So A dot B is like, there's a geometric significance that is like the projection, like this one, where like the absolute value, like these two bars, are like the magnitude, the length of this matrix, of this vector. The magnitude of A, or the norm of A, times the norm or magnitude of B, times cosine theta. So what is this cosine theta? So like we have A, and then we have B, that's the origin, and that's theta. So then we could kind of view this as we can kind of like view this as one unit. Like we can bundle B cosine theta, or we can bundle A cosine theta. So now then, if we bundle b cosine theta, then what this whole term really ends up meaning is the projection of b onto the not a, but the span of a. The span just means like this vector in like all scalar multiples, like ka. So like basically kind of taking this whole thing and like stretching it out into like an infinite line. So b cosine theta, this is theta, so like what that means is like we drop a perpendicular down here, and then this is like this length is b cos theta. Well, there's no need to actually do that. It's pretty obvious that like this right here, this distance is or sorry, this thing right here is the length. It's the line b cosine theta. Notice that we can also like, I'm treating this as like kind of the projecting b onto a, but of course you could also like, it's commutative, like you could kind of group this a with cosine theta and treat it as a projected onto b, but for now, like let's only assume that, let's only view it in terms of b projecting onto a just to stay consistent, right? Okay, so what is a dot b? Let's say that a is like, why is this true? Again, this video kind of does a nice job at it. I'll do it my own way, kind of to convince myself. So this vector A has like some entries A1, A2, dot dot dot, AK. And then if you dot two vectors together, then basically like their lengths have to be the exact same. So like B1, similar thing, dot dot dot, BK, and the dot product, of both of them is basically a sum of products from 1 to k, or I equals 1 to k, of AI, BI. Right now, let's just, how do I select and delete? Select, oh wait, never mind, sorry. Can we like just scroll down a bit? Yeah, we can, okay. So then, the key idea, like why on earth is this computation right here? Like, why does it give us this? Again, so this thing right here is the length of the project. Like b cosine theta is the norm b magnitude of b cosine theta is the length, the projection of b onto span. This it's the length of this, and we multiply it by that. So why on earth does this give us this? Now, that is a very good question. Why are these equal to each other? Now, I want to work with normal vectors. Like, I want to make, let's assume that a and b are both unit vectors with like the magnitude of a and magnitude of b are both 1. That's kind of like the case I want to start with. So first of all, like let's just assume that a and b are just normal vectors. Like if we have like a dot k b, where like KB is like the vector, like let's say like K could be 2, like A dot 2B. Like, let's just multiply B by 2, A dot 2B, right? Multiplying B by 2 is just like kind of doubling this. So like 2B. So we just double that. And then when we project this doubled B onto here, right? Like B projected onto A, like gives you like this length. If you double it and you project here, it's quite clear that like this length from here to here is double this. Oh, I can't undo anything? Yeah, I'm deleting everything I just did. So A dot 2B is clearly, just from visualizing this, like is clearly double of 2 times the dot product of A and B. So like we can double this, and then like, so by doubling B, we kind of double this length of the projection, and that stays the same. Now we could also double A. In that case, this B cosine theta, right? Its projection would stay the same, but then we double this magnitude, and then we'd still double the answer. So in general, A dot B, like we can kind of stick in a K, either here, or what am I saying? We could like scale A by J, and we can scale B by K, and then this thing is just J times K times A dot B. That's kind of that's the idea. So now I'm just going to assume that A and B are both 1. They're both unit vectors. And if I can show, and I'm going to show that like this, the dot product equals the like A dot B, when A and B are both unit vectors, its dot product, the scalar, like A dot B are 2 vectors dotted and returns a scalar, like just a number. And that number represents, geometrically, has an interpretation, which is the length of B projected onto the span, the infinite number line, the infinite line containing A, the projection of B onto this line, its length, times the magnitude of A. So I want to show that like that is the case. Now, for the case where both A and B are unit vectors, so in that case, A and B are both 1, so we're just left with cosine theta. So then, and cosine theta is literally just the length of projection of B onto A. So then, in this case, when these are both 1, then A dot B just equals cosine theta. That is, cosine theta is both the projection of B onto A and the projection of A onto B. But for now, we're only considering B onto A, right? So let's just that's our number line. Let's only focus on quadrant 1. Let's call this this vector, let's say that A is the unit vector in the x direction, right? Just 1, 0. And then B could be some unit vector here. And then like that, this whole thing is like a unit circle. So now so like B, like the vector B has an x component, bx, and a y component, by. So b is just bx plus by. That is b. And that is, of course, theta. So what is b dot a? B equals to bx by, and then a is equal to 1.0. Let's just say that, right? Then if we kind of plug this into this summation formula, then these two would like a dot b would then become bx, and then by times 0 would give us 0. Sorry, a dot b is not a vector. What am I doing? Is bx plus 0 equals to bx, right? So if a is just 1, 0, then b could be anything you want, any unit vector in this unit circle, and it dot a would basically extract its x component. Now bx equals the cosine theta. Like if you draw this triangle with b and then bx and by, and this hypot is 1, then cosine of theta equals bx over 1. So cosine like bx equals to cosine theta. In fact, by is clearly sine theta from this same right triangle equals sine. Oh, okay, I really cannot write right now. Sine theta, right? So wait, sorry, I actually realized that I did it wrong. I mean, this is correct, but like, what I want to do is I want to have a be the vector here, and I want b to equal 1, 0. So then in this case, a dot b would equal just a has ax, ay, ax. Now, clearly a dot b would give us ax, which is the projection of a onto b. But one of the key ideas is that, like, what is the projection of b onto a? Well, if we drop this perpendicular here, then like this ax right here, the length of the projection of b of a onto b is equal to is also ax. So the projection of a onto b is equal to the projection of b onto a. Like there's kind of symmetry about this this axis right here, which is one of like the nice takeaways I got from this video. But I mean, we can also see this geometrically. In both cases, like here we have like a right triangle with hypot 1, so we have ax, and then In this other, we have a second right triangle, which here, which also has the hypotenuse to be 1, and then so like, these are basically the same triangles except just rotated. So I've proven that, so ax, which equals, so a dot b, again to recap, gives us ax, which by this kind of symmetric thing means that ax is both the projection of a onto b, the length of it, and also the length of the projection of b onto a. One of projection of b onto a. And there's like a nice symmetry here where like the projection of one vector onto the other is the same length as that projection onto this. And we've done this for the x component. We can also do this for the y component, where like if b were to equal 0, 1, let's say that now b, like that is b, 0, let's do quite somewhere else. If we have b as 0, 1, 1 for b, and we have like some a right here, which is also a unit vector, then a can be broken up into a y and ax, well that's a right triangle, and that's b, so that's theta. So sine of theta equals, or ay equals sine theta. Like this is theta, and this is the hypotenuse of 1, so then that's just the, wait, sorry, what am I saying? SOHCAHTOA, the cosine of theta equals the adjacent or the hypo, which is 1. Again, this is the exact same thing where ax equals the length of projection of b onto a. And now in this case, a dot b equals ay, which again is a, sorry, what am I saying? This theta, forget this theta. Wait, never mind. But if we consider a separate theta, which is this theta right here, which a makes with the origin, then ay equals the sine of this theta, sine of theta, and this sine of theta right here, its y component, is equal to the projection of a onto b, but we care about the projection of b onto a, so we drop like this perpendicular down here, and this theta is equal to this theta. Just from simple geometry, we have a right-hand triangle here, right? where this is theta, and this is 90, let's call this alpha, and alpha is 90 minus theta, right? So we have like 90 degrees, 90 minus theta, so this must be theta. These are the same. Basically, it's the same approach. We have two right triangles right here, and we have like this triangle right here, and this triangle right here, and the symmetry line is there. So basically, like what I have shown in both those examples is that A dot B, if B equals to 1, 0, or B equals to 0, 1. In fact, like in multivariate calc, like this is actually known as I hat in linear algebra 2, that's known as J hat. Then A dot B is equal to the length of the projection of to B onto A. And magnitude of A equals 1, then we've basically proven this case, because when we do A dot B, where B is either has a 1 and 0, then that 1 basically extracts either the AX or the AY, the X component, so like the X component of A, or the Y, the X coordinate of A, or the Y coordinate of A, right? Like we have A, and A has like an X coordinate and a Y coordinate. So if we do like A dot B were 1, 0, then this 1 would select that. And then AX is both the projection of A onto 1, 0, but it's also the length of the projection of 1, 0 onto A. And there's a similar argument to be made for AY. So we've proven that. Now, the question is, what if B equals to any Bx, By, still a unit vector? Then the question is like, can this hold, right? Can this property, again, the property that we want to prove that this equals that, the dot product equals the projection, does this hold? Like we've proven it for both the I and the J, both basis vectors of R2 in this case. How do we prove it like for a general case? Well, I mean, one thing I'd like to note is that like A dot B is actually A dot B is in fact a matrix multiplication of A and B. So A dot B could be also written more, I guess, formally, whatever, as the matrix multiplication of A transpose B, where that's a 1 by K matrix, and B is a K by 1 matrix, and the number of columns of this matrix is the number of columns of that matrix. So we're left with so the result of a 1 by K, we're left to multiply the K by 1 by 1 by K from the left, and these K's like kind of, I guess not really count, like they kind of disappear and we're left with a 1 by 1, which is like a scalar, right? Now, Now here's kind of like this thing, like matrix multiplication is a linear transformation, right? Like we've kind of shown like a linearity in like in terms of different scalars, like a dot kb equals to like k times a dot b. And now what we want to do for like the other linearity is like the other like linear thing, like in linear algebra, like when you see kind of already common thing for like linear operators, I think like defined like this, like they're closed under scalar multiplication and kind of distribute like this thing right here where like b1 plus b2, right? So like we have a b1 plus a dot b2, right? Now let's just like in general, like if like kind of continuing off of this thing, like we've shown this. Now to show this, like it's pretty. I mean, I want to say it's almost like let's just say that we have like just this vector, just a, and we're projecting b onto it, where b is like this thing right here, right? B. Now we can decompose b into any two vectors. Like it could even be like this and this. Sorry, this is b. Now this angle here, it doesn't have to be 90 degrees. Like this could be an acute angle, right? But the whole point is to show this. Like the projection of b onto a, the length of that is this. Now we could have like b1 be this thing and b2 be here. Now they don't have to be 90 degrees. They could just be any two vectors that happen to add up to b. Now, what is the projection of b onto a? Well, it is clearly right here, right? This is like this is kind of how much b contributes to this answer. B1 contributes to a like b. I don't want to write it out actually. To be honest, I just don't want to write it out. Sorry about that. So like you have this result right here, which is the projection of b onto a, its length, and like if b is b1 plus b2, then b1 contributes like the projection of b1, or why is the one here? It's not a superscript, it's subscript. So the projection of b1 onto a is this much, and the projection of b2 onto a is this much. And together, the projection of b1 onto a, its length, that much, plus the projection of b onto a, that much, equals the projection of the whole b onto a. So like that's kind of visually how I see this, where like projection of like the composition, like a plus like b1 plus b2, like the composite vector by adding b1 and b2, like it's like if you dot it from the left by a to like get its projection onto a, well, we can kind of consider it, we can kind of contemplate the b1's contribution and b2's contribution, and like kind of this kind of relates a lot to like this like kind of explicitly writing this out as a matrix multiplication. Then ax and ay are basically kind of, if we do bx by, then we kind of like ax and ay, right? Like ax is the contribution of the case where like where we're kind of multiplying by the standard basis vector 1 0. I can't write y for some. Sorry about that. Like ax ay, like when we dot it by that, right? Then that kind of selects for that basically gives us ax. Okay, technically it's in a 1-by-1 matrix, and that's the significance of ax. If we have like this I hat, right, 1, 0, then like AX is the contribution of the, the X coordinate, right? The X coordinate, so AX basically extracts the contribution of the X coordinate of B projected onto the vector A, right? Like if this were BX instead, then this thing would become AX times BX. This is a multiplication, it's not a dot product. Now this makes sense because if this were 1, 0, right? We've already shown that like by this scaling property right here, right? I believe I've shown that right there. Like by this example that we're clearly allowed to do this. Like from 1, 0, we can just compress 1 a little bit by multiplying it by bx, which is between 0 and 1, and we get that, right? Same thing for ay. Ay is basically is what we get when we when we do ay, a dot, the j hat, right? 0, 1. So like if this is 0 and that's 1, then by doing this major multiplication, this zeroes out, and we just have ay times whatever 1 is, which is just itself, ay. So ax, ay, dot, multiplied bx, by. The a basically gives like kind of the x coordinate of a onto x, but by the symmetry idea, which we saw like right here, symmetric about this line, this ax, like ax is kind of like the projection of a onto the x-axis, right? But that's kind of the same thing as the projection of the x-axis onto a. So like ax kind of gives you the projection of both a onto b and b onto a. So it's like it gives you this contribution. Like ax gives you, like if we just have ax, we ignore, like we just hide ay and like we just view ax, this number ax, then what this does by like its contribution basically does ax bx, which essentially gives the contribution of this thing right here, like of ax onto the x-axis, and ay is the projection of ay onto the length of projection of ay onto the y-axis, and by that symmetry, it's also the projection of the x-axis onto a, and the y-axis 0, 1 onto a as well, by that symmetry that we've seen. So then bx, by, by dotting, like by matching these two, like we get like, so bx is like kind of bx is basically, it's gonna sound really stupid, but bx is bx times 1. Or like 1 is like this whole 1, 0, right? So like whatever we did here from like b equals 1, 0. So like if you had bx equals to like a half, right? Like 0.5 is bx, then like clearly this length projection of b onto this a is like some value here, and by chopping like bx to half of that, we get half of the length of this projection of b onto a is a half. So that's just like the scalar stuff, right? So then ax times bx ends up giving you how much xy's, how much in terms of the x coordinate of b contributes to the projection of b onto a, and then by times ay gives you how much the y dimension of b contributes to the projection of B onto A. And then this is linear algebra, so we just sum everything up, and we get the total and the projection of B onto A. Now, let's just actually visually, so like everything I said so far can be kind of viewed kind of in this video right here, but now I'm just going to add like my own twist to this, like a nice kind of visual thing to like put this all into perspective, like in a 2D case. So now, like, we're done, but let's just, like, this is A, right? And then we want to project B onto A. Again, they're both unit vectors for convenience. Now, B onto A is, sorry, if they're unit vectors, sorry, let me just start again, right? Okay, I think I can hold shift down and draw a straight line, right? Or not, wait, no. Actually, let me do this right. Right here, then another line, right there, right? Okay, so now we can have A, and we can have B, both unit vectors. So like we could draw a circle if we want to. Now, what I'm going to basically show is what I did right here, but for a right angle, and like make it convincing, because like there's no, like, this was a bit kind of ad hoc, but let's just do it right. So like the projection of B onto A, the length of that, is this, right? This length right here is the dot product of these two when these are both unit vectors. Now, B is, in turn, the vector B can be represented as the sum of Bx plus By. In fact, let me just write that out, right? B equals Bx plus By, right? So the whole idea basically is like kind of the same, like associate, whatever the second property is, like this cool thing, like distribution thing right here, like that's kind of like the heart of this. Like if you kind of if you just kind of like multiply both sides by a transpose, then we basically get A dot Bx plus A dot By, right? So I want to like, cause like this looks kind of nice. Like this is kind of like a nice algebra. Like we just do the same thing to the left side, to the right side. We do some, we distribute it. Like this looks pretty nice, but like let's just kind of like show it visually, which I'm attempting to do in this picture right here, right? I want to show that this. So like B onto A is this length, and then Bx and By. So what is X is like, so like projection of B onto A, its length, can be split up into like contributions from Bx and By. So let's kind of look visually at what is Bx, how does it contribute to this length right here, right? This is kind of like what we're trying to get, the projection, the length of the projection of B onto A. So B has Bx. So then if we kind of like drop a perpendicular here, this is a perpendicular, that's a perpendicular, then this length right here, right, from here to here is like Bx is contribution, or A dot Bx. Now again, let's recap. Why is this length a dot bx? Because we've seen this a lot by now, but that's bx, and that's a, and that's b. So like a dot bx is so bx is the projection of b onto this vector here, which is the same thing as wait, sorry. Basically, like let's go back to this. Bx here is a dot bx because, well, I mean, we've already discussed this quite a lot of times already, but like when you do a dot b when b is 1, 0, then we've established that a dot b, if b is 1, 0, gives you just ax, right? A dot b when b is 1, 0 gives you ax, which is the length of projection of b onto a. So if like this vector is horizontal and it's 1, 0, then if you dot it, then you get like, if we have a and we have 1, 0, then a dot 1, 0, a transpose dot 1, 0 just gives you ax, right? So like that's pretty clear. A dot 1, 0 just gives you ax, which is the length, the projection of a onto this, but it's also the projection of 1, 0 onto ax. So then a dot 1, 0 gives the projection 1, 0 onto that. Now this is 1, 0 right here. Like this whole thing is sorry, what am I doing? This whole thing right here is basically a unit circle. Well, so you have like a here and b here, right? This whole thing is basically a unit circle where that's 1 and that's 1, right? So then we have a dot 1, 0 kind of gives you this, which is also ax. Again, we can draw like a triangle. We can look at this triangle and that triangle, and the fact that they're both 90 degrees, and the hypot is both 1 in both triangle cases, because magnitude of a, the norm of a is 1, and then 1, 0's norm is clearly 1, 2. They're all unit vectors. Like this ax equals that ax. So we know that the horizontal unit vector projected onto a is ax, right? But then this bx is between 0 and 1. We're basically kind of taking this and we're like this ax, which is, we have 1, 0 unit vector, and we're just kind of like compressing, we're squishing it from 1, 0 to like, we're kind of squeezing this to a bx comma 0. We're squishing this. So by kind of squeezing this, like if we cut it in half, then we cut this thing in half too. So like, just like we know from 1, 0 gives us like ax, by squishing down to bx, we squish the dot product ax down as well. So we get ax bx, which is, I mean, ax bx. Like it's literally like ax, for the 2D case, ax bx plus ay by. I feel like the more tired I'm getting, the sloppier my writing's becoming right now for the 2D case. for 2D, right? I'm just showing this in 2D for like the first quadrant. There are 4 quadrants. The first quadrant where B is kind of not as big an angle as A. Like we could do the same thing for B here. So like there's 8 possible cases, 2 for each quadrant, B over under for all of them. I'm just doing one thing, but like for exercise for a reader, they could do it for all the other quadrants if they want to. Again, we're already done, but like I'm just convincing myself and hopefully the viewer that this thing holds for unit vectors in this quadrant for a 2D case. Okay, so to recap, B projected onto A gives you this, and then B is split into BX and BY, and like this thing kind of comes from like BX gives you this. So what's left? BY. So we want to show that BY projected onto A, the length of that projection is that. If we can show that like this thing right here is A dot BY, then what we have done is we've kind of visually verified that this thing holds true. That is, the length of the projection of B onto A can be viewed in terms of B's constituents. Like we break B into BX and BY, and we look at how much BX contributes onto A, and then we look at how much BY contributes onto A, and we sum them up. So if we get like this, the contribution of BX onto A, which again, I've shown like by squishing the 1, 0 case onto A, which we know is AX, then like we squish it by BX, so we get AX BX again, which is like D, I'm getting hyper, like AX BX, which is like squished of 1, 0 contribution onto AX, because like AX times 1 is just AX, which is the contribution of the projection of 1, 0 I unit vector onto A is just AX. And then by squishing the 1, 0 unit vector by BX, then we have to kind of like multiply X by BX, right? So AX BX, AX, it's getting really tiring. I'm definitely only going to do this one for this session. So like BX projected onto A, the length of that is clearly like just visually speaking, it's just this. Now why? So we have some, but like the projection, so that BX projection onto A's length gives you this much, right here, right? But then B projected onto A gives you here, like there's something more, and that something more is like we have this and we have that, right? But now there's something missing. We want to show that this missing thing comes from here. Like, so how do we show this geometrically? Right. I mean, well, what is BY's projection onto A? Well, um, 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 um. Right. I remember in the shower I figured this out. Okay, yes. We drop a perpendicular. Why did I do that? I mean, I know that if we take this BY, right? It's like this is not like, and you kind of drop it here, right? Then this, then this kind of right here is also 90 degrees. And then this thing right here is 90. That's equal to this. Like this direction is A, right? And then if we drop, like, if we kind of, like, this is a perpendicular, if we kind of drop this perpendicular from here, like BX, like if you consider like this line in the direction of A, like this thing right here is parallel to A, then I basically want to show that BY projected onto A, its length, is this. Now, Um, by projected onto, so like how do I show that by like projected onto a is this? Because clearly this equals this, because like this is a right triangle, like this is 90, that's 90, this is 90, so then, well, we know that like if we have like four sides, four corners, and three of them are 90, and this one has to be 90 as well. So like it's a rectangle, and like in a rectangle, like this side and this side have the same length, and then this side and this side are the same length. So clearly these both have the same length. So then all we have to show is that this is the projection of by onto a. Well, this is a, like this is like kind of a direction of a, right? And that's by. And then 90 degrees. So like right here between a and b, like we have this theta, right? That is theta. And that's 90, so then this thing right here is alpha, right? Now if this is alpha, then this must be theta, right? And if this is theta, then and this is alpha, right? Wait, no, what am I talking about? I hate geometry. Okay, let me just draw this again. It's getting too cluttered, right? We have A and we have B. They're both one-dimensional unit vectors. And B's projection onto A at a right angle is that much. And B's projection, B can be written as Bx and By. So B's projecting onto A is this much. Now Bx's projection onto A gives you like, that's Bx, and this is By, right? So Bx gives you this, and then By, what does that do? And this is 90 degrees. This is theta. This right here is alpha, like alpha equals 90, theta. I'm trying to draw theta. Oh my god, I'm tired. Theta plus alpha. They're basically complements of each other, right? Cosine theta equals sine alpha, and so forth. We're in degrees. I mean, I know that radians are what the cool kids use. So theta and alpha, so that's, and this is 90 degrees, then this in turn is theta, right? So then, since we have theta, then like, we have theta and we have like a right triangle, then like, it really makes sense to like drop a perpendicular, so that if we drop a perpendicular, then we have like theta here, and this angle must be alpha, right? So then this angle, like this line is, these two are parallel to each other. So like by projected onto A, right? By projected onto A is by, like, so alpha. So by, like, what is sine of this theta, right? Sine of this theta is the opposite, or cut to opposite or hypotenuse, right? So like sine of theta, right, equals to sine, like this angle right here, like between these two, equals like this length, let's call this kind of L, and that L, right, opposite over by, right? I'm just taking this triangle right here, right? This triangle right here, which is a right triangle, and that's like this angle is theta. So like sine of theta is this L. Again, this and this are the same as I've kind of shown above. So sine of theta is L over by, right? That means L equals to by sine theta, right? Wait, what? What am I trying to show again? I'm trying to show that L, this L here is the projection of by onto A. Wait, isn't that obvious? Isn't this picture the answer? I can't undo more, sorry. So then, wait, no, yeah. So like, sorry, I think I've just been, okay, so this is A, right? And this is B, right? So B's projection onto A is this right here. That is the projection of B onto A, its length. Now, we can kind of split that from B onto this. We can split it in terms of the contribution of Bx onto this, its projection, and then Bx's projection onto A is we drop the perpendicular, and that's that's the contribution from Bx. Bx A dot Bx, and this is kind of this whole thing is A dot B. And now the question is and then all we need to show right now is that this is A dot by. We want to show that by. We want to show that again, B projection onto A gives you this whole thing, right? This whole thing is B's projection onto A's length. Now, it can come from, we can kind of decompose b into bx and by, and then we have to kind of view bx's contribution this much, and all we have left to show is that y's contribution is that much. So what is by projected onto this line, onto this vector? The idea is to like kind of take this and like kind of, we drop a perpendicular, right? Dot, dot, dot. We kind of like drop like this thing here, right? And this vector, like this vector here for a, this is just like, this is also the vector a. Like it's just like, it's also like a, but like scaled, moved around somewhere. It's like something here, right? And then by, like we can take by right here, right? From here to here, and we can set this as our new origin. So we can like kind of draw by again, right? Like basically take by here, like this is 90. So however much by is, we kind of move it back up here, and then we project it right there. So that's by. And then by, or sorry, well, another technique we can do is, let's just delete all that. It's getting too cluttered. One other way of doing this, like this is by, right? And we kind of, so like, recap. We took by, and then like at the tip, the arrow, we kind of drew another a. So like we want to basically show that like this length, the missing length from ABX, we want to kind of add some contribution to get like the full projection of B onto A. So like what I want to do is I want to show that like these two lengths are equal, that the projection of BY onto A is equal to this, because clearly this and this are equal just based on like this is 90, that's 90, this is 90, this must be 90, so a rectangle and rectangle, two opposing sides lengths are equal. So now like I dropped, so again, so I want to show this equals this, and then we're done. So by, right, what we can do is this is our head, like by's head is here, its arrow is here. We can kind of take by and we can kind of add another by, right? So that's also by, right? That's by here. This is 90 degrees. And then now the projection of by onto this A is quite clearly this right here, right? And now this length, if we can show that these two lengths are equal, then that's the projection of by onto A. And if that equals this, and we know these two are equal, then we know this equals this, and that's clearly the projection of by onto A, because like if this is theta, and this whole thing right here is alpha, and clearly like this whole thing right here is also alpha. Wait, okay, so this is theta, that's alpha. If you have a perpendicular line, then sorry. Oh, I mean, I just know visually speaking that this line equals this line equals that line, we're done, but how do I show that this line equals this line? Well, we have this line here, right? And we have this line here. Like we have like this kind of A angle here, and like we have a BY kind of hitting here, and then going on, right? And like we kind of dropped a perpendicular here to get this. And then if we drop like kind of right here, right here, because like that's also perpendicular. It's a like, cause like this line right here is perpendicular to A, and this is also A. So like this is perpendicular, and that's perpendicular. So like this angle here equals this angle here. So like we have this height. We have this height right here. We know that equals this height. And we know this angle here equals this angle here. We know that. We know this is 90 degrees. this is 90 degrees. So then, so this height, like we have a 90 degree triangle, and we have the hypotenuse equal to each other, which is by. And if we have the hypotenuse and we have a 90 degree triangle, and we have this angle here and this angle here, then we can like, okay, so then this angle is this angle, and then like this angle here must be equal to this angle there. So like this angle x, this side length x, like let's call these angles theta. Then cosine of theta, right? Cosine of this angle here is like this side x over this hypotenuse right here, by. And that's by too, right? By. So this side here, x, equals to by cosine theta. Now this theta is just in this picture here, like theta, like that's just right here. And now this x right here, right, like cosine of this theta, like from here we have cosine of theta, right, equals x, this thing, divided by by. This equation right here, x1, and that's x2, right? So like x1, like both, so like from this we get x1 equals that, and from this we get x2 equals by cosine theta, right? We have this, we have this. So from that we can deduce that x1 equals x2. Thus we have shown that this length here, which is clearly the projection of the length of the projection of by onto A, is equal to this, which is also equal to this. And the projection of by onto A is just A dot by. So now, like, visually we're done. We have A, we have B, we have the projection of B onto A, which is this thing right here, and we've kind of shown that, like, we have like a bx, and we have a by. We dropped a perpendicular from B onto A to get that projection. And then if we look at like B as bx and by, and like we look at bx onto A, and we get like something here, which kind of like B's projection onto A is like this length, and then we can kind of split it. We can kind of we can kind of look at its kind of the contribution, like the projection of B onto A can kind of come from the contribution of like bx onto A plus the contribution of by onto A. So like this right here comes from this thing right here comes from bx onto A, and this thing right here, like if we take this point right here and then we take this A angle, like whatever this A is, and we kind of like split this here, like we kind of draw another thing, like which is kind of Also, let's just make A stretch. I don't know, let's just like make like a super A, which just goes forever, right? And then like we kind of drop another line that goes in the same direction as A, right? Then what we can do is like we can look at this line like BY, right? Like we know that this side must equal this side. And then BY, we can kind of double here to like also have BY. And we can drop a perpendicular down here. So like right here. So then BY, like we have like this line here, which is the direction of A. We have like this as BY. Then it's pretty clear that like this like projection of BY onto this span of like this line that's in the direction of A will give you like A dot BY. And that thing just equals this. I mean, I'm not good at geometry, but it's pretty clear that like this equals this because like this and this had the same like this like these are both right triangles. They both have hypotenuse of BY. They both have right triangles, and then this angle equals this angle because like that's just from basic geometry. And, like because of that, we can like use cosine onto this angle to show that this angle, that this side equals this side, the length of this side equals length of this side, and this is just by dot A. So then this is by dot A, and then this is like by's projection onto span A, by's projection on span A, by's projection on span A. So this right here is by's contribution to A dot B, and this right here is bx's contribution to A dot B. And now we're basically done. I believe I've at least shown that like A dot B can be viewed as the projection of A dot B, two vectors, same length, is basically like a transpose of B. And then what that gives you is that gives you the length of the projection of B onto A scaled by the magnitude of A. So AT dot B, like we have A1 dot 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 AK times whatever, like this is B, but like in general, like if we have like some entry BI, right? Like this BI basically kind of like if we have AI right here, just some ith entry onto A, and then we're just to like dot it with like everything here. Like this is more than 2D. This is n dimensional, right? Or k dimensional, I guess, right? So like AI, and if we consider like in a standard basis where like everything is 0 except for the ith entry, like this is i's index like from 0 dot 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 to I, or from 1 dot dot 1 index, we start A1. So AI, what the meaning of AI is, like when we're taking AI and we're kind of dotting it by 1, like this 1 would basically extract AI and 0 everything out. So the entries of A in A dot B, like A dot B, can be viewed as A transpose times B, and then each entry in A, like the ith entry in A, is in fact the projection of AI onto the axis, onto like AI, the significance of A of I is just a number, It is a number that is what you get if you take this like 0, 0, like the standard like one vector in the standard basis for r to the I, right? Like we have a standard basis of like we have basically like an identity matrix of like all ones, right? And like everything else, all the other entries are 0. And then we have like the ith entry here, like the ith column right here of the standard basis that's our standard basis for r of I. And then we basically like take this like one of the ith standard like vectors in the standard basis, which kind of gives you like a direction, the ith direction, right? So AI, this entry in the representation in the coordinates, like the yes, this can actually be viewed as coordinates, where like AI is like the coordinate of like the projection of A onto the ith vector. Like let's just call a standard basis. Let's just call this like um I'll call this like um u of I, like the unit vector in like the ith dimension. Like you have like 0, 1, 1, 0 for like I hat, j hat for like x and y for like standard basis. This is like the standard coordinates. Like basically we have k dimensions, and then like this is the ith axis. Like we have like instead of like a 1 dimension graph and a 2 dimension, a 3 dimension, we have like all sorts of dimensions, and then there's a particular ith dimension, and we have like a unit vector in that specific like direction, like dimension that it the ith dimension. And then AI is but the length of the projection of AI onto that standard dimension. And by the symmetry, if you have like that one in all zeros, AI is not just the it's both the projection of A onto this UI, but it's also the length of the projection of UI onto A. Basically, it's like the same idea of like how we have like this kind of symmetry here. Like these are both of these are like unit vectors. The projection of like this guy onto this one, the length of that projection, right, is equal to the length of the projection of this one onto this one. So like this thing from here to here is equal to this thing from here to here. So AI, the number AI, represents the. It's kind of like when you do a AI, like a dot whatever this thing is. This number basically gives you like however much contribution from this axis of B. So like now instead of 0, 1, 1, 1, 0, like we can like replace this with BI, or like basically like B1 dot 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 BI dot 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 BK. We have K dimensions, right? And we have like AK and like dot 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 like AI, and we start off with a A1, then the AIth entry of A basically corresponds to like when we dot that with B, then like BI basically scales unit vector, like scales down like 0 dot 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 1 dot 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 scales UI down by BI. So like so AI, right? So AI times BI basically gives you like the contribution from BI towards like B's projection onto A, because like we're basically taking B, and then B is but some like in your RI, like these basically give you the coordinates of B with respect to like the standard basis of RI, and then basically they're K like different like coordinates like k different directions, and then b is but the is it like the coordinates of b, basically these entries basically give you like what they mean. Like one way of looking at them is just they give you the coordinates of b, like how you define the coordinates of b. Like b has like stretches in all these k directions. It stretches in the b'th dimension, like bi, like that's how far on the ith axis in the ith dimension you go, bi, right? It's a unit vector, so all these entries are between 0 and 1, right? So then like this ith dimension, when you take this and you consider how it contributes to like projecting b onto a, then like that's where like this AI comes in. So like AI, like BI and AI, like what they do is they basically kind of like AI basically gives you the like AI right here. What it does is like it'll take this like UI, this vector in the standard basis, the ith vector of the standard basis, and like AI, when you kind of dot it by this thing, it would give you the projection of AI onto like BI, but also the projection of BI. I mean, also projection of the unit vector or UI onto AI. So like the projection of AI onto UI is the same thing as like UI onto AI. There's kind of like that symmetry going on. So like this whole thing right here, like so then like BI, like by introducing BI instead of like 1, we're basically scaling it down by like whatever coordinates, like how B is, like however much like this coordinate of b is with respect to this ith axis and ri. And then when we're dotting, like when we're so like what AI ends up doing when you're doing this matrix multiplication out is it will basically give you this AI times bi ends up giving you the projection, the contribution of the projection of b onto a by bi. Because again, if like bi were 1, then like this dot, like the projection of a onto the ith axis will be given by AI. And now we're just taking this axis, the unit vector, and we're scaling it down by bi. So that will, so like by doing AI times bi, what we end up getting, like AI times 1, just AI, is how much AI's projection onto the unit vector UI in this ith dimension. So AI times BI, like we're scaling, like B basically scales down this vector. So this basically gives you the contribution of BI projected onto A, right? And that's just for BI. That gives you like some bit right here, right? And then what we have to do is we have to basically kind of, it's linear algebra. We just have to like, linear algebra, just the whole sum of products, right? Like the products of sums of products. So like basically kind of sum that over all of the I, and then we end up getting the projection of B, the whole B, onto A. We basically sum all the contributions of each of like the components of B, the BIs, onto A. We just do AI dot B times BI, and we just add them all up, and that will give you, in total, the length of the projection of B onto span A. And that, all of that basically kind of justifies this for me, and we can kind of view it as a matrix multiplication. And then there's actually like I'll close by showing like like in this book there's like a on a what this is the second edition of linear algebra done right, and then in the chapter 3 linear maps, there is um, there is like in chapter 3 linear maps in this book, uh, there is like a section called the matrix of a linear map on page like 5051 of linear algebra and Wright's second edition. Like there's kind of a precise definition of matrix multiplication as a composition of two operations. Like it's like kind of like the whole chapter 3 of this book, like linear maps, like kind of like what a matrix means, like how what like matrix multiplication is as like kind of like basically what is a matrix, right? Like that's kind of like what this chapter 3 kind of talks about. It explains like one view of a matrix as how you transform a standard, like how you transform a standard basis. Like it just talks about like multiplication as a composition of two different like a composition like if like matrix like m1 times m2 times some vector v is like m2 times v, and that whole thing left multiplied by m1, and like basically like that's what like it just kind of talks about like what matrix multiplication like truly means, like in terms of like where each basis like where all the bases like end up in terms of other bases, and like what a matrix even is. Like a matrix like M, like all the columns basically are like all the columns in a given matrix are just like what you do to like what the action you do. Like so if you have a matrix like that takes Rn to Rm, like basically like it takes like the columns of a matrix are basically kind of um like they like kind of specify where each vector of a standard basis goes in terms of like coordinates of like another standard basis for next. But basically, the end story is I highly recommend that you kind of read this book, like at least up to chapter 3. Um, yeah, I think that's all for now.